Hey everybody, this next video lesson is going to talk about a couple of mini gas laws. Last video lesson we talked about a big combined gas law that combined all the variables of pressure, volume, and temperature, but these are going to actually isolate only two variables at a time. And so we'll first start about talking about just introducing the laws to you. So the first one is going to be Boyle's law, and then the next one's called Charles' law, and finally the third one's Gay-Lussac's law. And each one of these we're going to be discussing or looking at the behavior of two different gas variables. It's the same three gas variables, but one of the variables in each of them is held constant. Now I told you about how to do problems involving constant variables in the last video lesson, but now we're going to actually take a look at them graphically and be able to distinguish between the three gas laws when a variable is held constant in each. In Boyle's law, we will take a look at pressure and volume holding temperature constant. And in the Charles' law, we will take a look at volume and temperature holding pressure constant. And finally, Gay-Lussac's law takes a look at pressure and temperature and holds volume constant. So let's take a look at these three mini gas laws and take a look more closely at the graphical representations of each. What you're looking at is Boyle's law. Boyle's law is a relationship between pressure and volume. And if you remember, this graph should look very familiar to you because you did it in the gas law lab that we used to introduce this chapter. If you remember, you took a sample of gas and you squeezed it by reducing the volume, and the pressure went up. And you pulled out and stretched out the volume so that the pressure went down. In each case of Boyle's law, you're going to hold temperature constant, and of course particles are still held constant. And the relationship looks a lot like the combined gas law with temperature being held constant. And as we talked about in the previous video lesson, if you hold something constant, you can cancel it out of the math, and what's left is P1V1 equals P2V2, and that is Boyle's law. Now it's an inverse relationship, and you saw this when you did the lab. As you lowered the volume, the pressure went up. As you squeezed the gas into a tighter and tighter space, the pressure inside the container increased. And as you stretched the volume by pulling the gas into a larger and larger volume, the pressure decreased. And so these two are in indirect or inverse relationship to one another. As pressure goes up, volume goes down. As volume goes up, pressure goes down. It's important to be able to identify the gas laws not only on what variables are associated with that law, but also what the graph looks like, because you may be expected to sketch a graph of Boyle's law in the future. A practical example of Boyle's law is any time you are trying to decrease the volume in something. Like let's say you take a balloon and you grab the balloon with two hands and you try and squeeze it, or even a basketball for that matter, and you're trying to squeeze it, and when you push on it, it pushes back against you. That's because as you decrease the volume by pushing on the basketball or the volleyball, the pressure increases on the inside and it pushes back. And so that's an example of Boyle's law. You've got something that has variable volume and variable pressure, keeping the temperature inside pretty consistent. But as you squeeze the volume decreases, the pressure increases, and that's an example of Boyle's law. The next gas law that we're going to talk about is called Charles' law. And Charles' law was not represented on the gas law lab at the beginning of the chapter. And the reason is because in order for you to experience Charles' law, you have to have a substance that can change temperature and have variable volume. And that's very difficult to do. But in Charles' law, pressure is held constant and the number of particles is held constant. And so you're looking at a relationship between volume and temperature. And what you can see graphically is that as the temperature increases, the volume increases in a linear relationship. It is a direct linear relationship. It's key, though, that when you look at Charles' law, that temperature must be in Kelvin. We're looking at absolute temperature, not degrees Celsius. In the absolute temperature scale, you can't go lower than 0. And theoretically, at 0 Kelvin, you should have 0 volume. But a sample of gas will increase its volume or take up more space the more and more temperature increases. Unlike Boyle's law, which was a decay sort of trend, we're looking at a direct linear trend. It's important to know the difference between Boyle's law and Charles' law. The graphs look obviously different, and also the variables are different, and the one variable that gets held constant is of course different as well. A practical example of Charles' law is take a balloon Have you ever left a balloon in a cold car overnight, or maybe in a cold room, maybe in a room in your house that isn't heated very well, and you come back, and after it's cooled off a little bit, it shrivels up. The balloon kind of drops in its volume. It's kind of lumpy and didn't hold its air. Now the air didn't escape from the balloon, but what happened is the temperature inside the balloon dropped. And so when it did that, the volume inside dropped with it. So what you get is a shriveled up balloon that doesn't look like it was inflated to full volume. But it's not because the gas escaped. We held the particles constant, and the pressure inside remained fairly constant, but the temperature went down, so the volume went down. The last mini-law that I'm going to talk about is called Gay-Lussac's law. Gay-Lussac's law is a direct relationship between temperature and pressure. And this is the other example of the gas law. This is experiment number 2 that you did in the gas law lab. In that lab, you had a test tube of gas, and you capped it and started heating up the gas. So the volume remained constant, and so did the number of particles inside the container. And so the volume, which is rigid glass, and the particles stayed inside. But as the temperature increased, you should have seen the pressure go up with it. And what's nice is that it's, again, a direct linear relationship. So if you double the temperature, the pressure should double. If you triple the temperature, the pressure should triple. Of course, the temperature must be in Kelvin, just like it was in the last gas law, the Charles law. Temperature must always be in Kelvin for these gas laws to be represented accurately. And so in Gay-Lussac's law, pressure 1 over temperature 1 equals pressure 2 over temperature 2. We're holding volume constant, so it's not included as part of the law. A practical example of Gay-Lussac's law would be like a basketball that's left out overnight, and you go and try and dribble it in the morning. In the cool morning air, the pressure inside the ball has gone down because the temperature has gone down. Or maybe you've heard of somebody inflating their tires in cold weather, and as the friction of the road heats up the air inside the tire gets higher and higher and higher pressure. They always tell you never inflate a tire with cold air, because as the temperature gets higher, the pressure goes up and may burst the tire. So you might be asking yourself, what do you need to know from these laws? First of all, you need to be able to identify the law by name based on the variables involved. The second thing you may be asked to do is to sketch the graph, including labeling the axis. And the final thing I may ask you to do is simply identify the graph based on what you see, keeping in mind that some graphs represented to you may not represent any of the gas laws, or in other words, it's an impossible relationship. And here's what I mean by that. If I give you a graph and I show pressure versus volume, you should first think to yourself, Boyle's law, all right? Because Boyle's law is a relationship between pressure and volume holding temperature constant. Then you should say, well, Boyle's law is an inverse relationship. Does this graph represent an inverse relationship? The answer to that is it sure does. Now, what if I give you a graph that has pressure and temperature in a linear decreasing trend? You'd say to yourself, well, that might be Gay-Lussac's law, because Gay-Lussac's law has pressure versus temperature holding volume constant. But that's a direct linear relationship, and this is an indirect linear relationship. And so this, in fact, is a relationship that cannot exist. And so be able to identify a gas law by name, or be able to identify an impossible gas law. That takes care of this video lesson. Thanks for listening.